Welcome to video lecture number 3, which covers section 1.2, day 2, graphs of equations. As always, please take a moment to read today's objectives. The first part of this video lecture covers material associated with objective number 1, and those are the intercepts of a graph. So if you'll please write down the definition of the intercepts. While you're doing that, I'll say a few words about the graph, the picture that you see on the right, and then of course how you find these. If you look, all of the points in the red are examples of x-intercepts. So in this particular graph I've drawn, there are 3 x-intercepts, and then there is 1 y-intercept. Now the number of intercepts changes depending on what the graphs look like, but the most important thing you need to know is how to find these things. So if you don't have a graph and you're just working with an equation, remember to find an x-intercept, you're going to let the y be 0 and just solve for x. To find a y-intercept, you're going to let the x be 0 and solve for y. And if you're wondering why that is, I think looking at the picture above can kind of give some further clarity. All x-intercepts always have a 0y coordinate, so that's the first thing we're going to do in the equation is set y equal to 0. So take a minute to write the rest of this information down, and we will move on to example 1. Example 1 asks us to find the x and the y intercepts of each equation algebraically, meaning you're going to have to show some work by hand. It says confirm your answer graphically using your calculator. So I'm not going to show you that in the video, but there is a way where you can graph it on the calculator and confirm that these answers are right, and we'll talk more about that in class. However, for now, let's take a look at example 1a. I started by writing down that we need to find the x-intercept first. Now you can find the y-intercept first. I've just chosen to do x-intercept, but we're going to need to do both. So remember from the definitions, all x-intercepts have a 0y coordinate. So we're going to let y equal 0 in the equation, and that's what I've done. And then we're going to work to solve for the other variable. That variable is x, and that's what we're looking for. The first thing I notice is that 0 divided by 5 is simply 0. So now we have an equation that reads 0 equals square root of 1 minus x. The next thing that I'm going to do is get rid of the square root symbol. You may recall that to do that, we're going to square it because a square root has that same radical value. So we will do that to both sides, and our next result will look like 0 equals 1 minus x. Now from here, we still need to get x by itself. I need to move the 1 to the other side. So to do so, I'm going to subtract 1 from both sides. Well, that will now give me the equation negative 1 equals negative x. Well, x is still not by itself, so I need to get rid of that negative in front of the x. To do so, we will divide both sides by negative 1. This ends up giving us the statement x equals positive 1. So if I write that as a point on a graph, remember that we originally set y to 0 at the very beginning, and we just found x was 1. So in this particular case, there is only one x-intercept. Now I'll show you how to find the y-intercept. To find the y-intercept, remember that we let the x value be 0, and we plug that into the equation, and then solve for y. So in this case, I notice on the right side we have the square root of 1 minus 0. Well, that's just the square root of 1, which turns out just to be 1 itself. So the next version of this equation we could write down would be y divided by 5 equals 1. Now the last thing we'll need to do in this case is get the y by itself. To do so, we're going to undo the division by 5 by multiplying by 5, and remember, whatever you do to one side of an equation, you have to do to the other. So at this point, we've reached the end. Y is by itself completely, and we get y equals 5. Now remember, we let x equal 0 to begin with, and we found y to be 5, so the point on the graph that we would be looking for would be the coordinate point 0, 5. So why don't you go ahead and please try example 1B and 1C, and we will check those in class tomorrow. Example 2 is our first look at a word problem that is describing the height of a baseball as our y after t seconds of being hit, and given an equation, y equals negative 16t squared plus 96t plus 3. What are we being asked to do with that equation? It says, assuming nobody catches the ball, how long will it take for the ball to hit the ground? Well, important to note is that the ground, the height of the ground, which is y in this case, is actually 0. So what we end up doing is plugging in 0 for y. And what we want to find is that time. Well, anytime 0 is y, remember what we're doing. We're simply finding the x-intercept. So all this is an x-intercept question in disguise. Now, unlike the other examples, this one is a little bit more complicated to solve using algebra. So instead, we will use our graphing calculators, and in class tomorrow, I'll show you a step-by-step demonstration of how you find x-intercepts using your graphing calculator. For now, try to complete example 2 using your graphing calculator. If you don't know how, you can wait until tomorrow and we can discuss it then. Part 2 of your notes deals with symmetry, both graphically and algebraically, and all of these problems relate to objective number 2. Let's start by talking a little bit about x-axis symmetry. You have a few diagrams here. Let's focus your attention to the one on the left. I've written some notes about what x-axis symmetry looks like, and you can see the picture. And clearly, notice that if you have a single x value, if you get two opposite y values from that single x, say that this is the point 3, 7, and the point 3, negative 7 is also on the graph, what we end up seeing is x-axis symmetry. Some other things that may help you understand this are that with x-axis symmetry, the same x's produce opposite y's, so that's another way of describing what I've written in blue on the graph. And also, remember, because this graph would fail our vertical line test, remember from last year that if a vertical line can cross a graph at 2 or more points, then it's not a function. And also, last but not least, is this folding idea. If you were to fold this graph along the x-axis, what you would see is that both of these pieces of the graph would match up perfectly. So there's kind of 3 ways to look at it. So let's move on to y-axis symmetry and origin symmetry. For y-axis symmetry, notice from the picture that when we have opposite x values, they produce the same y value. For instance, this could be a quadratic or a parabola centered around the y-axis, and that would have y-axis symmetry. Some things to note also is that these graphs are functions, meaning they do pass the vertical line test, and notice that folding along the y-axis in this case, if you were to fold right down the y-axis, this graph would match up perfectly on both sides, creating the illusion that there was one piece to this graph. So again, there are 3 ways to think about the y-axis symmetry. The third type of symmetry is origin symmetry, and notice I didn't write anything about folding here because that really doesn't apply to this case. What the key is that you need to notice is opposite x values will always give opposite y's. Therefore, if you have the point on the graph, for example, 3, 4, then a point that will also have to be on the graph would be -3, -4. Notice both x's and y's are opposites of the other point, and this would have to be true for every single point on the graph. Like y-axis symmetry, this is also a function because any vertical line that we run across the graph will only touch the graph in one spot, so indeed it is a function. So what I just said is kind of summarized in the box here, and I encourage you to take a moment to read through this or look back to it at any time that you need to help you determine whether a graph has x-axis, y-axis, origin, or no symmetry at all. So let's move on to example 3. Example 3 asks us to determine what type of symmetry the graph has, if any. So I'll try example 3b with you, and notice I've copied it down and labeled one of the points as -5, -6. We'll start with x-axis and y-axis symmetry. To determine that, the easiest way graphically is to look at the axes x and y. Notice along the x-axis, if I were to fold along that line, I would not get 2 equal halves to that graph. The same thing can be said if I were to fold along the y-axis. I would not split that graph right down the middle. So, therefore, both of these are a no. Now, I would like you to write some form of an explanation of why that is, as you just heard what I said. The next one would be origin symmetry. To do that, I would notice that the point -5, -6 is on this graph. If it has origin symmetry, well then the point 5, 6 must also be that graph, on that graph, sorry. Rather, if you look, 5, 6 is clearly not on this graph, so that's a no as well. In this particular case, this graph has no symmetry whatsoever. Now that you've seen example 3b, please try example 3c and 3a on your own, and we'll check them tomorrow. So you've been shown some ways to look visually at a graph and determine whether there's some symmetry. However, there's also ways to do it when you don't have a graph and you only have an equation. There are some algebraic tests for symmetry, and those are listed here, and there's a test for each type of symmetry. And so with those, I've shown you a little diagram that may further explain what's going on here. So just for example, if you want to test an equation for x-axis symmetry and you don't have its graph, what it says is that you need to replace y's with -y, and you will get the same equation. And I think really the difficulty is, well, why is that? Why is that true? So if you look at the graph, I think it gives a better explanation. When I replace y and -y with each other, notice regardless of which one I use, I'm going to get the same x value. So that means the rest of your equation would look the same. That's all that's trying to say. And the same can be said if you look at the pictures for 2 and 3, which describe y-axis and origin symmetry. So feel free to write that down if you need further clarification. If not, let's go ahead and skip to example 4. Example 4 asks us to algebraically test each equation for the 3 types of symmetry. So we're not going to look at the graphs at all. Rather, we're just going to deal with the equations to test for symmetry, and you do need to be able to do both. So this one's a little unique because when you square root to begin this problem, you need to square root both sides, and when you do that, when you square root an equation, remember that there's this plus minus. We tend to forget that. And what that really means is you have 2 equations in one. We have positive square root of 6 minus x, and we have negative square root of 6 minus x. So there are 2 equations that we have here. Now let's start with the test for symmetry. So I've decided to begin with x-axis symmetry, and I've written down the original equation. Now, according to our test that we've listed above, in order to check for x-axis symmetry, the first thing we're going to do is replace y with -y, and we're going to see if when we simplify, we end up getting the original equation. Well, to simplify, we need to get that y by itself. So to do so, we're going to divide both sides by -1 to get that y alone. Now, when we divide the right side, the plus and minus, by -1, remember, we're really dividing a plus by this negative down here, and then we're dividing a negative by this negative down here. And what happens is, when we do that, we'll get y on the left, and we end up getting plus and minus once again. The positive turns to our negative, and our negative up there turns to our positive. So notice, when I compare this equation With the original equation, they are the same. So in this case, yes, there is x-axis symmetry. Now, if you would try y-axis or origin, you'll notice that you wouldn't produce the same equation. So once I've found a symmetry, we don't have to go further with finding another type of symmetry because a graph will only have one of the three types. This concludes video lecture number 3, so I ask that you would try example 4A and C on your own and have those ready to check for tomorrow. And additionally, the final page on the back asks you to write at least one question you still have after watching this video. Please take a moment to do that as well, and we will discuss your questions tomorrow. Thank you for watching, and good luck.